Within 25 years, human beings will fly out into space and land on the moon. We know this is true. Man will conquer space. The Johns Hopkins Science Review, presented by the Johns Hopkins Institutions and WAAM in Baltimore. This is the Johns Hopkins University, famed for 76 years for its contributions to learning and scientific research. Here in the many laboratories, Hopkins scientists are probing into the secrets of science, which, when discovered, will be translated into benefits to be enjoyed by you, the people of America. Each week, we are privileged to look over the shoulders of today's scientists and catch a glimpse of their research. On this, our 178th showing of the Hopkins Science Review, we present the first episode in 3 programs, showing how man will conquer space. To introduce this program on space travel, here is Lynn Poole of Johns Hopkins.
I have an airplane ticket here in my hand, and this airplane ticket is for a round-trip flight from Baltimore to Los Angeles. Now, if I offered it to you, you wouldn't be amazed. You might be happy, but you wouldn't be amazed because those flights are usual every day. But I wonder what you'd say if I offered you this ticket. Now, this ticket is for a round-trip passage, a round-trip flight to the moon. Now, it's a first-class ticket, and if I actually offered it to you, you might tap your head and point at me. But if you did, you would be wrong, because such a ticket will be used one day. Because one day, man will fly from our Earth up through the atmosphere and out into space and will land on the moon. Haven't you ever daydreamed about such a trip? If you have, come with me in your imagination and imagine that you are on a rocket headed outward into space. What would you encounter out in those regions?
Your rocket will leave the ground with a tremendous roar, gaining greater speed as it rises higher and higher. Passengers will look back at the Earth as the rivers and flat plains grow dimmer and dimmer. They will peer down on our highest mountains, which will then appear to be nothing but tiny anthills on the face of the Earth. Still looking backward, the space-bound passengers will see the Earth as it grows smaller and smaller, as it begins to fade in the distance. But as the rocket ship hurtles through space, the passengers will look through the forward portholes, will peer through the strongly shielded windows on the sides, and realize for the first time how vast is this limitless area we call outer space. As they speed along, they will know that around them, millions of miles apart, are 9 major planets. Our Earth is one of these planets, all of which are cold and can be seen only because they reflect the powerful fiery light from the sun. Next comes Mercury, Venus, our Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and finally Pluto. Perhaps the passengers will catch sight of some of the few billions of meteors in constant motion in our solar system. They will see the stars, which, unlike planets, give off light. And stretching millions of miles beyond our solar system are other solar systems, known as galaxies, tremendous clusters of stars which take their place in the vast area of the total universe.
Well, it's a mighty big universe, isn't it? But before we can use this ticket and go out into space, we must force our way up through the Earth's atmosphere. Well, now, what is this atmosphere? How high does it go? how far does it extend? And how far have scientists gone in learning how they can push their way through that atmosphere? Well, now, let's leave our fantasy and let's come right down here on Earth. And let's talk with the scientists and find out what are the facts. What are the facts about spaceflight? Well, now, there are questions which must be answered and can be answered by someone well-versed in astrophysics. And one of the people that can answer those questions is the director of the Laboratory of Astrophysics and Physical Meteorology at the Johns Hopkins University, Dr. John Strong.
The Earth's atmosphere is very interesting, Mr. Poole, especially the upper air, which separates the region where we live and navigate from the vast emptiness of space. It is like this. This is a globe which represents the Earth, and this is a canopy of the upper atmosphere which protects us from the ultraviolet light and meteorites of outer space. The air in which we live and navigate is densest at the surface of the Earth, and it gets thinner and thinner as one goes higher and higher in the atmosphere. You are all familiar with the problems which this thinning of the atmosphere poses for mountain climbers and for aviation. When you travel by plane and take off from the ground and rise to 3,000 feet altitude, the air is thinner, but you are still comfortable and safe. At 5,000 feet altitude, you will notice the air is getting thinner, unless the pressure in your cabin is regulated to remain the same as it was on the ground. At 10,000 feet, you must breathe supplementary oxygen to remain comfortable. At 20,000 feet, it is necessary to have supplementary oxygen to remain alive. Beyond this, both pressurization and oxygen are required. Without them, you could not live, even a short time. Let us consider the structure of the atmosphere as the astronomers and rocket scientists do. First comes the troposphere. This is the cloudy part of the atmosphere, and it extends up to about 10 miles height. It gets colder and thinner the higher one goes. Next comes the stratosphere. This extends to about 60 miles height. Although it gets thinner, it remains almost constantly cold the higher one goes. Finally comes the ionosphere. This layer, extending from 60 to 120 miles in height, gets its name from the fact that it contains electrically charged particles, or ions. These ions are useful to man, since many radio stations could not transmit beyond the horizon of their antennas if these ions did not reflect or bounce the radio waves around the curved contour of the Earth's surface. Beyond the ionosphere, our atmosphere compares in thinness or emptiness to the best vacuum man can produce. Beyond the 120-mile boundary of the ionosphere, you are in the region called the Exosphere, which extends outward to infinity. In the Exosphere, where man will make his expeditions in space, he will have to be protected from harmful ultraviolet rays and meteorites. The oxygen and ozone in the protecting upper air filters out the most harmful short wavelength ultraviolet rays. Billions and billions of meteorites dart out of space each day in our atmosphere, but fortunately they do not bombard us at the bottom, because when they enter the upper atmosphere, their swift motion creates a friction and causes them to be heated, ignited, and burned to harmless dust before they penetrate to the Earth's surface. Only the largest ones reach the surface, and this only occurs rarely. Thus, if it were not for the protecting canopy of the upper air, the unfiltered ultraviolet rays, and the falling unimpeded meteorites would destroy every living thing on Earth.
But now, so far we have seen something of this vast universe of ours, have seen the layers of the atmosphere through which we must push our way to reach space. And we realize that we must protect ourselves out there against the flying meteorites, against the ultraviolet rays, and many other things which might harm us. Well, now, we know that a vehicle can carry us out there one day, but before we can send men out there are certain problems which must be overcome. And these are problems, these are hazards, which the scientists must overcome and must solve before we can go into space. Now, to discuss these problems and these hazards of life, we have brought for you from California a well-known astrophysicist who can answer many of these questions for us and tell us with what we must contend in space. He is from the Institute of Transportation and Traffic Engineering of the University of California, Dr. Heinz Haber.
You're correct, Mr. Poole, if you say that the engineering problem is only half of the story of conquest of space. There is also the human question. We must ask ourselves, will it be possible for man to survive in space? Will he be able to live if he is pitted against the utter void with no oxygen? There is no atmospheric pressure. There are all sorts of radiation, ultraviolet, cosmic radiation, and he will also be without weight. He will be floating without weight. Now, among those problems, the oxygen problems has been with us for quite a while. And we are happy to have tonight one of the newest developments, and this development will be shown to you by Dr. James Kennedy, who brought it down from right field where the suit has been devised and constructed.
Thank you, Dr. Haber. This is the Air Force T-1 altitude suit. It is the result of 6 years of research and development by the personnel of the Aeromedical Laboratory at Wright Field. This suit has been designed specifically to protect man against the hazards of exposure to extreme altitude. At 50,000 feet, unless man breathes oxygen under increased pressure, he will not survive. Above 63,000 feet, the fluids in the human body will boil at body temperature, and this will cause gaseous locking of the circulatory system and death within a few minutes. This suit is not an experimental garment. It is a production type suit and is being worn by about 150 people, Air Force and civilians. It has been worn on every high altitude flight of the X-1 rocket research aircraft, and on one flight, this aircraft was well above 50,000 feet and its cabin pressure was lost. The suit inflated automatically, delivering the oxygen from the emergency oxygen cylinder to the mask and to the suit, preserving the man's life and allowing him to live. I'll now have the Sergeant Lichty inflate the suit so you can see how it looks at altitude in the event cabin pressurization is lost. You'll notice moisture. Ordinarily, we prevent that by heating the face piece. Mr. Bill Bridgman wore this when he flew the Skyrocket to 79,000 feet. This man is not as nimble as a ballet dancer, but he can do his job if necessary.
Such a suit would come in mighty handy in case, in a flight in the upper strata of the atmosphere or eventually in space, one of those meteorites would come along. This piece, cosmic matter, at one time has traveled about 40 miles per second, and he might have punctured, and it could puncture the hull of a ship easily, and then an explosive decompression would result, against which such a suit would be a very effective protective measure. Now, besides the oxygen problem, we have spoken of radiation. Now, there are essentially two kinds of radiation that might be harmful to man. One of those you have experienced yourself on the beach when you got yourself a bad case of sunburn. The sun emits ultraviolet radiation, and I have here a source, a flashlight of ultraviolet light, which I should like to show to you. We can't see this type of light. However, it can be made visible by a fluorescent screen similar to the ones you have on your television screen. Now we have to put out the light in order to make this visible. I point this source against the screen, and you can see that the screen is bright. Now let's try this piece of paper. If I interpose this between the source and the screen grows dark. This shows that even such a flimsy medium as this sheet of paper is able to stop these rays. Now similar devices would have to be used later in front of the windows, the portholes of a ship. A simple piece of plastic also stops these rays, and it's a good way of stopping these rays with these simple means. However, ultraviolet rays are not the only ones. We have also to deal with cosmic radiation. These are atomic nuclei that come from the depth of space, plunge into the atmosphere, and in their passage through the air, they produce all kinds of secondary rays. I can give you an example of how these rays act. I have here a Geiger counter. It's a type instrument that is used in atomic laboratories and civil defense. Every time a ray passes through this instrument, you hear a click in the loudspeaker. Now let us try the piece of paper, whether we can shield it off. You see it still goes on, so it doesn't work. How about this piece of steel, half-inch thick, which is pretty heavy? Let's shove the Geiger counter below. Let's see what happens. You see the clicking still goes on. It shows that we cannot protect people against these radiations unless we use very heavy armor, such as 6 to 8 inches of aluminum, and of course such weights cannot be carried aloft. So we must ask ourselves, will there be any danger from these cosmic radiations? The answer is that we don't know. Not yet have we exposed experimental animals to this thin spray of cosmic radiation, and we are not yet prepared to pronounce space radiation safe. Now concerning the oxygen problem, it will become critical only in a case of an emergency. Concerning the radiation, man has no senses for their presence. So a man flying into the high altitude and eventually in space will, in the beginning, not find much difference between a normal high altitude flight or an actual space flight. There will be one thing, however, that will remind him drastically that space flight differs from conventional aviation. He will, upon leaving the atmosphere, he will become weightless. And this will be a very strange experience at best. Space and weightlessness will become synonymous like desert and thirst or Arctic and cold. Can you imagine what it will be like to exist in a realm where there's no gravity, where there's no up and down? Man will literally be suspended on a universal flying trapeze, rising, falling, twisting and turning. Unless kept anchored to a chair or bunk, weightless man will helplessly float about the entire space of his confining cabin. Now it is a matter of common knowledge that weightlessness is brought about in space, but equally common are the misconceptions, how this comes about. Some people believe that if we detach ourselves from the Earth far enough, finally we may reach a point where the gravity becomes negligible. Or it is argued, if this would represent the moon, there is a point in between the two bodies, about here, where the action of the two bodies pulling in opposite directions cancel. However, this is not the case. Weightlessness is brought about by lack of support. And you all have felt weightlessness, or at least reduced weight in an elevator. When it starts going down, the rope slacks, and then you are being deprived of a certain amount of support, and you get this strange hollow feeling in the pit of your stomach, which tells you that you are about to get weightless. Weightlessness is actually not an attribute of space. I want to show you a weightless bottle right here in the studio. I can do this simply by taking away the support from this bottle. Now if I do this, it falls down. Now I will make it differently. First, let us take the bottle and see how it looks like when it is weight. When there is weight. The water is about 800 times heavier than the air, and if I shake it and get some bubbles into the water, you see they come up immediately because the water is heavier than the air. Now, I do the same thing, but I'm going now to pitch the bottle way up into the air. I hope I won't drop it. And then you watch the bubbles that float about in the bottle because they're weightless, they will stay there. Let me do it again. Once again. You see, this is weightlessness right here in the studio. Now, if man will enter a spaceship, he will then be just like one of those bubbles. He will float about in space, and he will then be weightless, such as these bubbles right here in the bottle.
Things are floating in space because they have no support, no pull from gravity. So, like the water and air bubbles in the Gallen jar, objects in space have no weight. At first, the experience may be such a shock that the spaceman may claw desperately as he tries to get hold of something. As his spaceship is in free flight, or as he floats outside a space station, he will have to overcome this psychological reaction of fear to this weightlessness in order to carry on his work. This means that psychology will play a part in space travel. It will be a problem to be overcome. Our actions are based on accustomed body coordination, based on lifelong experience with gravity. This coordination will fail us out in space. The first quick movement of a man rising from a chair will send him coasting off into space. But man's aerial antics are not the only floating objects to be considered. Tools, pencils, and even the paper on which he keeps scientific records will float around the cabin of the spaceship unless securely anchored. To overcome this, all metal instruments must be made of steel, or at least have a steel strip on the instrument. These can be held snugly in place when pressed against a magnetized panel, similar to the magnetic board which holds knives for the housewife in her kitchen.
Now all this may sound and look a little funny to you, but actually behind these things there are some questions we have to answer. We must assume that man will have some trouble in controlling his body movements under conditions of weightlessness. He may even become disoriented. But how about circulation? How about digestion? How about breathing? Will it be possible? Can, for instance, somebody eat upward, something like that? Now, for that purpose, we have here a young lady. She's standing on her head, and you see she drinks against the force of gravity. And this is possible because these functions, also such as circulation and respiration, are being powered by elastic forces, which do not require the help of gravity. These conditions and these functions do actually go on undisturbed was shown in some experiments made by high-altitude research rockets. You see here, rocket rising and animals, monkeys and mice, have been brought above by these research rockets, and just like the bottle which I tossed upward a minute before, the monkeys were weightless, however much longer, because the rocket is a better tosser than it can be better done than with this bottle. And these animals lived through, and this has shown that the normal physiological functions are not grossly disturbed by the lack of weight. Now we must ask ourselves, are we justified to do such research, spend money and time on these studies? After all, the next flight to the moon is in no way around the corner. It will take quite some time before the first man will fly through space or even land on an alien body. But many of these problems of high-altitude flight are similar to those in space flight. I have here in my hand a model of the Duckless Skyrocket, which was flown to an altitude in excess of 70,000 feet. Now this craft, if I tell you that it was that high, actually was some sort of a spaceship. 70,000 feet gives not a good picture. Let us express it differently. At that altitude, 96% of the atmosphere were below the feet of the pilot and only 4% were above. At that height, he had all the problems of the oxygen. He had to wear the suit, and if he would have flown another 50% higher, he would have entered the realm of the cosmic radiation. And so the problems of space, the human problems, are gradually creeping in. And still we can say that we are flying through space with these rocket aircraft, although we can do it only for a few minutes.
As Dr. Haber has pointed out, one of the first problems, the first step toward reaching space, is satisfying ourselves that men can live out there in space. They must be protected against the meteors. They must be protected against the ultraviolet light, the cosmic rays. They must be provided with pressure suits so that they can live and live comfortably in this space. All of these men are working on the scientific facts. These are the facts about space travel. Now, of course, the next step is how are we going to construct a rocket that will reach out into space, out into atmosphere. And we believe that engineers will be capable of constructing a rocket that will penetrate our atmosphere and reach space.
Astronautical engineers tell us they can construct such a rocket. How will they build it? What will it look like? How will it be propelled? How fast must it travel to leave this Earth? We hope you will be with us next week when Dr. Francis Clauser of Johns Hopkins University and Dr. Martin Summerfield of Princeton University show us how astronautical engineers plan to build a spaceship, when they tell us step by step how this rocket will be catapulted out into space. Be with us for the second chapter of How Man Will Conquer Space. The Johns Hopkins Science Review is produced by Lynn Poole in association with Robert Fenwick and Warren Whiteman. Directed by Paul Kane. Associate Director Ed Serro. Art direction is by Barry Mansfield. Your narrator has been Joel Chaseman. Parts of this program have been mechanically reproduced. The Johns Hopkins Science Review originates in the studios of WAAM in Baltimore.
This is the Dumont Television Network.